Okay. Um, I hope everyone can hear me okay. My name's Noelle Garza, and today I'm going to be talking about strategies for managing uncertainty when we're working in process design. And so this is obviously going to be a focus on in process simulation. There's going to be a lot of uncertainty and a lot of effort that goes into general process design, but this is a focus on using your process simulator and how to manage uncertainty when working in process simulation. So just a quick note before we get started. This is a famous quote by a British statistician who argued that mathematical models are used to try and understand and predict the world around us, but they're not going to be perfect. It's not a great representation of reality all the time. But if we're uh, mindful of what we're using and what we're doing, it can be quite useful. And so process simulators like CHEMCAD are used to model real world processes using mathematical models because we want to be able to predict outcomes. And, there's always going to be some level of uncertainty and some error carried over because the real world processes can't be perfectly predicted. But, you know, by thinking about the areas where we expect higher uncertainty and how we can combat this as much as possible, then we can achieve higher confidence and reliability in our process simulations. Um, so this is an overview of what we're going to be talking about today. Obviously, we're focusing on the ChemCAD aspect of this, but I'm going to be talking to you in the beginning of the webinar for the first half, basically about the uncertainty in process design and the background information, the goals, and how we can achieve these goals. And then in the second half of this webinar, I'm going to be actually opening ChemCAD and trying to demonstrate the different tools we have available to you to manage uncertainty using ChemCAD. And so the first thing to consider is our input to ChemCAD. The input data, it could have measurement errors, or maybe we're, making assumptions about the experimental or field data. It could be that this data that we're putting in ChemCAD is calculated and not actually measured in the field, a calculated value. It could be the mechanisms like reactions taking place and what is driving the reactions. Are there side reactions, things like that. We try to simulate behavior in ChemCAD from what we know and what we understand about the world. So if we don't know a lot about what's going on and there isn't a lot of literature data about this process, it's going to be likely that a simulator like ChemCAD is not going to know things that you don't know and capture the exact correct behavior. So we have to be mindful of what we're putting into the simulator and what we're expecting um, to get out of it. So that's introducing errors from the inputs that we have in ChemCAD. But what about uncertainty from using the models? We have to make assumptions about our process and how to choose the models, which is the right model to choose. So the uncertainty around, the selections that we're making in the simulator um, is going to be introducing uncertainty into our overall process because, errors are propagating and the wrong choice will give you poor results. And then finally, there's uncertainty around the design. So even if we do all the groundwork of what we're putting into the process and the right model selection, there's still uncertainty around like what's feasible in our design. If you're designing something from scratch, sometimes we don't see a clear path for a feasible design to our process. So all of these things together are all the uncertainties that we encounter when we're working in process simulation. So let's think about how we can reduce uncertainty. And to do that, let's first talk about our goals of the simulation. The cool thing about ChemCAD is if you don't know a lot and you just want to do these kind of rough back of the napkin calculations, a ChemCAD can do that for you, and you just manage your expectations of like how accurate the output is. Or if you have really, you need a lot of accuracy and you want to build a high fidelity model, that's going to impact like how much you're putting into the software and and how much effort you need to do like the groundwork to make the model very predictive of your process. So in any case, whether you're doing kind of lower fidelity or higher fidelity modeling, um, doing all of these processes to manage uncertainty allows you to build confidence in the process models and the outputs that come out of the models that you're building. And we're trying to approximate real world processes, and we're trying to optimize our processes. So it'd be great to have, improved accuracy and with risk management. So understanding where these common sources of error and uncertainty are, helps us be more confident in our models and kind of minimizes the risk of error propagating and getting, garbage outputs and things like that. So these are our goals, and it's up to you to decide exactly how much effort you want to put in to get the most accurate answers out, is essentially what we're trying to say here. So strategies to combat some of this, is to first gather experimental data, or if you have an actual plant data, if you have a plant in process and you can take measurements for it, if you can run some experiments, or if you can gather literature data, that'd be great too. So gathering data as much as you can is going to help you uh, understand the expectations of the outcomes of the outputs that you're getting from this. And sometimes we do get errors in this data though. So that's another thing to think about, is even though you're gathering data, it's important to quality check the data that you have, because there could be errors in that data. And I mean, it could be the data's a measured value. So in one example, uh, crude oil composition gets measured from the well, and they can only measure using GC analysis up to a certain carbon chain, like very, very high carbon chains, C50, C80, C200 if you have a really heavy oil. Sorry, I was getting a call on my computer. So if you have a very heavy oil, the actual machine that you're using to get the composition out is there's limitations to like how heavy that heavier fraction is. Like it can't do that measurement. So they actually have to calculate and extrapolate out the residual part of that oil, because they can't, like their machines just can't do an analysis and get the exact composition of the heavier components. So that's just one example of, like, sometimes we get data and it's actually calculated and not measured data. And even if we are getting measured data, it could be that our process is not in like a pseudo steady state. I mean, obviously it's not really ever going to be in steady state, but when we want to take data, we want to make sure that it's in as close to steady state as possible, for the expectation that we have for that process. And so something to consider with the data that you're receiving is, like, was it measured correctly? Was it calculated? Is this good quality data, essentially? And um, the other thing is, if you can't find data, you can also consult experts who have the background knowledge in what the behavior of the process should be. And it's just important to understand, when you're simulating a process, what the expected physical behavior could be, so you can recognize when something's not behaving correctly, right? So um, engineers don't always have the time and money for experimentation or for expertise. So, maybe there's just not a lot of literature data, or you're doing a feasibility study and you don't have physical plant data to look at. What else can we do? We can impose constraints. We can perform sensitivity studies. We can use probabilistic methods, which are gaining popularity, but they're not as popular. But right now, sensitivity analysis is a very common tool to help us test out, like using the simulator to test out feasibility and how our process behaves when we change different variables, so that we can get kind of a good holistic view of our process. So that's just general talk about, strategies to managing uncertainty, but you're here for, how to apply these strategies in ChemCAD Process Simulator. So we're going to look at a few tools available to you in ChemCAD. First, we're going to start with before building your flow sheet and you're, thinking about what you're going to input to the flow sheet and what, if you have data, what data you've gathered and the behavior you can expect from your process before you're building your model. And so that's involving the uncertainty around thermodynamic behavior and how to use ChemCAD to test thermodynamic behavior and choose the right model. So there are a lot of different K-value models to choose from in ChemCAD. K-value models are mathematical representations of the vapor and or liquid phases of a mixture. And these models are based on physical effects, thermodynamic constraints, or they can be based on loads of data that have been, they've tried to fit to loads and loads of experimental data and said, okay, this is kind of how this process behaves using a mathematical model. There's no one size fits all model, a universal model that's going to be precise and accurate for every situation. So that's why we have so many choices available to you, and it's up to you to kind of investigate and figure out which model best represents your process. So beware that the wrong model is not going to describe your process accurately. It's definitely worth your time to investigate the different models. And again, we have tools available in ChemCAD that I'm going to show you how to use and what to use for that. But essentially, we can break down these different models into equations of state, activity coefficient models. Equation of state are usually good for gases, like real gases, and solutions that just don't have interactions like polar components or azeotropes. They're used a lot in hydrocarbon processing. They're great for hydrocarbon or high pressure gases. And just something to keep in mind is if you have polar components, if you have azeotropes, move on from the equation of state. It's probably not going to do a great job. The activity coefficient models are what are used when you have when you do liquid separations, when you have non-ideal liquid solutions, and you're trying to predict liquid-liquid equilibrium for like distillation, for example. The activity coefficient models use binary interaction parameters, BIPs that are fit to data. We need to make sure that in order to get accurate behavior for distillation, for example, we need to make sure we have these binary interaction parameters and we can regress to real data. We can regress these parameters to real data. There are some specialized models down here in the corner, which are appropriately named for glycol dehydration processes or amine treatment, electrolytes, things like that. So if you have any of those in your process, I mean, it's worthwhile to investigate those models. And then finally, we also have some combined models. The VTPR is volume translated Peng-Robinson. Peng-Robinson is an equation of state. And the PSRK is, the P stands for predictive, and SRK is another equation of state. So it's a combined equation of state and activity coefficient models. And it uses something called a mixing rule to modify the parameters so that the equation of state is better for non-ideal mixture behaviors. Like, for example, they're doing really well for supercritical fluids. So important questions to ask to consider the best choice of what components are involved is what, do I have polar components? Am I using, do I have hydrocarbon components? What phases are involved? Is there vapor liquid equilibrium, liquid liquid equilibrium? What's the pressure range involved? So some of these models do better for very high pressure. Like I was saying, the combined methods are doing well for supercritical. So, think about the high pressures, high temperatures, non-ideal conditions, polar components, things like that, because some of these models lose accuracy, at very high pressures or something like that. So we can make adjustments to these, but uh, choosing the right thermodynamic model is an entirely different webinar. So this is just kind of some background information. Hopefully it's helpful to at least get the wheels turning. And so if you're unsure exactly which model, even after you've done some research and you're still it's unclear which model you should choose, ChemCAD allows us to test different models using TPXY chart tools, which I'll show you later where that is in ChemCAD. And, if you're not sure about whether azeotropes form, and what components are forming azeotropes, we have a tool called the azeotrope report, which will help you identify that. TPXY charts help you with that as well. But we just have lots of charts and tools that help you visualize your process and your thermodynamic behavior that will help you make the right choice for your process. Okay, so you might be asking, the thermo is not meeting, if you have real plant day, for example, and the thermo is not meeting your expected behavior, um, you can try different models out or adjust the parameters using regression. So again, we don't have time to really dive into applied thermodynamics, but just know that if you do have real data, plant data, measured data, literature data, and you need to adjust your model to match that, it is certainly possible to do that in ChemCAD. And you can reach out to support team, or hopefully we'll have another webinar on that, because I think that's a pretty hot topic people are interested in. Okay, so how do we manage uncertainty in ChemCAD? First, we work on building the model before building the flow sheet. So investigating thermodynamic behavior, making sure we have a good idea of the outcomes before then, moving on to building your flow sheet and then addressing uncertainties in the design and the ability to add flexibility to our process and things like that during the design phase of building the flow sheet. Okay, so, oh, it didn't. Oh yeah, okay, sorry. It did look like it didn't change slides on my screen, but uh, data reconciliation is something that is done after you've built the flow sheet and you've built the thermodynamic model and everything is converged. Um, it's not necessarily the next step after you build your thermodynamics model. I didn't want that to be there to be any confusion around that. I just thought that because we're talking about modeling and data and um, matching your process to real data, I would slip this topic in here because sometimes people don't realize this is available in ChemCAD. And I mean, you can and probably should do sensitivity analysis before you're doing data reconciliation, um, but I'll just go ahead and bring up data reconciliation now. For those of you that aren't that familiar with it, it just means adjusting your model to match real plant behavior. And again, it starts with a converged steady state model. The model should already have decent thermo in place where it's matching the expected behavior. It's just like similar to what Mr. George Box, the statistician, said, it's not gonna, these mathematical models can't exactly match processes because they're generalized to expected behavior. So if you have real plant data and you want to match the ChemCAD results to that data, you can do this kind of simultaneous parameter regression to match the process data. And so the result is your steady state simulation has been adjusted to match your actual plant data. And this is a piece of the puzzle if you've heard of digital twin technology, a big piece of that puzzle is data reconciliation. You have your, process simulation constrained to first principle physical models, and you're improving that to match real real world behavior, real world data. So this is a piece of that puzzle in that digital twin. Um, if you have like high fidelity models that you're hoping to reach to get very very accurate outputs. Okay, so that's just a little side note about data reconciliation. Again, that's after you've built your flow sheet and you've selected the right models and you're getting decent behavior. And we're just focused on really getting great matches to our data that we've collected. But moving on to sensitivity analysis, which is probably more commonly used, although in my experience, it's not used enough. I mean, there's so many ways to take advantage of sensitivity studies. It's really a great tool for running a lot of quick what if scenarios when you're dealing with uncertainty. And I'll talk to you a little bit about, the different ways that that sensitivity test study can be used. It helps with our uncertainty in the inputs that we have in the process variables, as well as in design and feasibility. Like, is this process seeing a path forward to building your process? So I'll show this in a demo later, but just an overview of sensitivity analysis if you're not that familiar with it. Um, they allow us to explore the relationships of the variables, and these are sometimes very complex systems. I mean, in CHEMCAD, you can just have, one or two union operations, or you can really build out a full plant and have very complex simulations. And so sometimes these complex relationships between the variables are not that easy to visualize and understand. So we can run sensitivity studies to check response to the input variables that we're uncertain about, and like a feed stream or a utility stream flow rate. And so these sensitivity studies help with model conceptualization and like heat integration and feasibility and variability of input variables and all these kinds of things. So I love sensitivity studies, and I really think it's an underutilized tool. So just a, a side note though on the distribution methods that we have available in ChemCAD, because a lot of times um, if you've ever run a sensitivity study before, you're probably using the linear distribution method. And so this is where you just vary the outcomes for a defined number of steps or step size. It's usually you're just looking at the overall prediction of the process. So you're not calculating a lot of values. I'm a visual person, so I like looking at plots, but you can look at charts too, and it's just helpful to visualize like, how the behavior of the process is going. And we also have though normal distribution. So if you remember from a grading scale, you have that bell curve. That's a called a normal distribution. And it's basically just that the outcomes are centralized around an average. So you tell ChemCAD what you expect the mean value to be and a standard deviation, and you get this sort of normal distribution or the bell-shaped curve. And it's helpful to visualize using a histogram, because you can tell ChemCAD to do hundreds or even thousands of calculations to kind of visualize the random values that ChemCAD is predicting for your process. It makes more sense when you see it. So I'll go ahead and jump into our demo of ChemCAD. Now I've been talking long enough about what to expect. Okay, so this is what the ChemCAD interface looks like. I'm going to start with a distillation process. So I think I'm already in it. Yeah, IPA distillation. So in the interest of time, I've already got a simulation open where I've selected the components that I'm going to be using: isopropanol, water, and hexane. and I've got Uniquac as my thermo model. And so now I'm just going to investigate um, the thermal behavior for this process because I'm uncertain about how this model selection is going to do for my process. So I'm actually going to want to recover isopropanol, and I know I need to perform a distillation. So one thing I can do is check whether I have azeotropes. So if we go into the thermophysical tab, there's this azeotrope report tool. And I've selected all my components so I can see whether I have binary or ternary azeotropes forming. And I can also choose different K value models, say if I'm not totally certain whether my selection is going to be able to predict azeotropes. So I can add another row and say NRTL is also a very popular activity coefficient model that can predict azeotropes. So let's say I'm going to run a report using these two models. So I click OK, and CHEMCAD predicts the reports. To get to the report, I go down to the bottom of the screen here. It's in this tab. And so it's telling me that my binary azeotropes are formed and which components are involved. It's also telling me I have a ternary azeotrope forming. And with the other model as well, it tells me information about, first of all, whether or not azeotropes are forming and where they're forming. So it's a really useful tool if you're concerned about azeotropes in distillation processes. Another useful tool, I'm going back to home, is charts. So I was talking to you a bit about using TPXY diagrams to investigate thermal behavior. Um, I'm gonna just select isopropanol and cyclohexane. Let's see what that is. Uh, Usually TXY diagrams are preferred because they provide a clear picture of the temperature dependent behavior of azeotropes, which is critical when you're designing distillation processes. So I'm going to leave it on TXY. And again, you can investigate multiple different thermo models here to compare. And in this case, just to show you what it looks like when you choose a model that isn't predicting azeotrope and giving you unrealistic results, I'm going to choose an equation state model that can't handle azeotropes, as we talked about. So I'm going to say OK. Okay, so here's my TXY chart that ChemCAD is showing me. And oh, interesting. So Uniquac and NRTL have azeotropes at green and blue. So down here, they're a little bit different in the prediction, but at least they both have predicted the azeotrope in a similar place. You're not getting the correct behavior with the Pang-Robinson equation of state though. So it's just TXY diagrams are really useful in investigating thermal behavior, and it's really useful if you have measured data as well. You can add this using the user series functionality. You can add those points to your chart and see whether the model is doing an accurate prediction. Just a side note, also, if you're doing azeotropic distillation processes or liquid-liquid equilibrium, the binodal charts are also very useful, or residue curve maps. They can just help better understand separation processes. So yeah, investigate the charts available to you. These help you visualize what's going on in your process before you're actually building your simulation. But I'm going to leave it at that just because azeotropic distillation is actually a difficult task. So we do have some examples in ChemCAD and that you can take a look at, and there's detailed notes on that. So so I'll just leave you with that. If you go to uh, with every installation of ChemCAD, if you go to open, and it's usually installed under documents, my simulations, and an examples file. Every installation of ChemCAD will come with a pretty extensive example files. And so we have some um, distillation processes here for you, examples for you to help you get started with that. Okay, so that's managing uncertainty in choosing a model, selecting a model, getting your model to as accurately as possible reflect your real process. The other main tool that I wanted to talk to you about was, of course, sensitivity study. So I'm going to close this out and open this gas turbine example. And just in the interest of time, I've got a pre-built example here for you. There's a lot of resources in the ChemStation's YouTube channel if you want to, if you're not that familiar with process simulation and you want to look at the ChemCAD essentials and helping you build the process from scratch. We have some tutorial videos available for you on that. But just in the interest of time, this is a pre-built example. Um, in this case, we're trying to build a flow sheet, but we're in the early stages of design and we have a lot of unknowns and uncertainty around defining the variables. So if we're uncertain about these variables and we're uncertain about our flow sheet design, we're going to use sensitivity analysis. So this is a gas turbine example. We have pressurized air and some fuel, methane going into a combustion chamber, and we're trying to ultimately, you know, start small and then converge the simulation a little bit at a time and build complexity into our model. But the best practice in process simulation is piecewise simulation. So right now, I'm focused on solving for my airstream. I don't know how much air is going into my process. I do know the composition of my streams. I do know the flame temperature expected for the piece of equipment that I'm using, based on my understanding and some research that I may have done. But again, I'm not sure about the flow rate. So I can use a controller. So I'm just going to insert unit op and drag a controller here. And if you're unfamiliar with a controller, it's basically like a goal seek function where I can tell it, in this case, I'm going to feed backwards because I have it downstream of my, in the exhaust stream basically, and I'm telling it to seek uh, the flow rate of air that I might have coming in. So I'm going to do feed backward for adjusting my air rate. And again, I don't know exactly what air rate there's a lot of uncertainty around that, let's say. So I'll just do like a wide range of minimum and maximum value. And then I can tell it, I do know that my flame temperature is going to be, um, let's say 2500. So that's going to be stream 10 temperature. And it's adjust airstream flow rate until exhaust stream temperature is 2500, let's say. And then I say, okay. and run all, and my controller didn't converge. And that happens a lot when you're uncertain about design and the feasibility of the design. And, you know, in the early part of this PowerPoint slides, I showed the Jenga tower because a lot of times in process design, it's like, how much can I build with as little information as possible before the whole thing collapses? So that's where sensitivity studies really shine in trying to figure out, what the answer is, because I don't actually know. And so I'm trying to solve for that, and I'm trying to get my process to solve and converge and give me good answers and real answers, and when I have, as little information as possible in this case. So I could uh kind of manually go in and adjust and say, well, let me do a new guess, and that's going to not be very efficient. So that's where sensitivity studies come in. And so that's under the analysis tab. I'm going to call this my error rate sensitivity study. And again, so my error rate is being adjusted, and I have to tell it to choose the stream and the mole rate. And so this is what I'm adjusting. And when I was talking to you about the distribution methods and sensitivity study, these linear distribution methods are the most common, especially when you're doing like feasibility design and you're just trying to figure out, things that you have uncertainty about. Linear distribution methods are very popular and then very useful. So, and then the other methods are more like the random variables where you tell it to calculate thousands of values, and uniform real value is assuming that all the random variables have equal probability, whereas normal distribution is centered around that mean that I was talking about, mean and standard deviation. So anyways, in this case, we're fine with linear distribution method. It's good enough. So in this case, I'm going to start with 1, and I can say vary it until, I don't know, 5,000, and I only need a 50 data points to kind of visualize what's going on in my process, let's say. And then so this is defining the error rate, and then I need to tell it that my dependent variable is going to be flame temperature, which is my stream 10 exhaust. Okay, so now I run sensitivity study for that. And I can, if you prefer viewing in a chart, you can use a report to view results, or like I said, I'm a visual person, so I'm going to do a plot, and I can see here how my air rate, chokes the flow of my combustion, and so I needed to increase my air rate to get this expected flame temperature. And this is just a simplified example to help everyone wrap their brains around how you can use sensitivity studies to help you with uncertainty in your design process. So now I can go back into my controller and say I need to at least be like 24 to 26 or 28, and it just helps me narrow down the range to get it to converge. And so, yeah, now it's converged, and oops. And so I've got my flame temperature close to 2,500, which was what my expected behavior was going to be. It was what I told the controller to calculate the airflow until I get that. So again, this is kind of a simple application of sensitivity study. We also have the distribution methods, the probabilistic distribution methods like Monte Carlo analysis, and we have this example here, which Monte Carlo analysis in simple terms is just a way to explore the different combinations of our adjusted variables, assuming that there is random distribution. And we have a couple of examples. This is one that you'll find in one of those example folders that helps you explore your process before you want to run an optimization. So in this process, we want to run an optimization to minimize the compressor power requirements for our process. And before we run the optimization in the solver, which is also found under this analysis tab here, we have this kind of optimization tool that will help you optimize your process to minimize your power requirement. But if you want to visualize if there's optima and where the optima is, you can run a sensitivity study, a probabilistic sensitivity study like Monte Carlo. And so I'll just click edit here. I've already had it set up in the interest of time, so we can explore the independent variables. These are the things that we're adjusting, and we're checking the outcome. That's the dependent variable. So the outcomes that we're interested in is the total power calculated for this process. So the distribution method for the independent variables is selected as a uniform real value, which is just saying that that there's equal probability for all outcomes, basically. And again, the normal, I'll just show I wouldn't use normal in this case, but the normal distribution will require you to tell it kind of where the average value is expected. And this is great when you're looking at, for example, a composition, which will have it's a natural fluctuations in it. You expect your composition to behave to have a certain molar breakdown, but if through natural variations, you're going to have different expectations. So you expect a mean, you might accept a certain amount of standard deviation, and then you can look at the histogram from that output. So in any case, okay, we're running low on time. So that's just to go to show how valuable sensitivity studies are. I think that people are not using them as often as they could be used. So just keep in mind that there are lots of different ways you can use sensitivity studies and lots of different distribution methods that you can play around with to see if that helps you with your process. The other thing that we talked about in managing uncertainty was data reconciliation, and that's also here under the analysis tab. There's not a lot of time to go into the process of data reconciliation, but we do have this really helpful paper. If you go to the ChemStation's website in the Knowledge Center, and it's under batch. So estimating simulation parameters for batch columns, and there's a very detailed information about setting up a data reconciliation. And so this is using an example of it's a batch column, and they have an actual experimental setup where they gather data and they can do a data reconciliation. So if you're really interested in doing data reconciliation, it's worth a read, and maybe you're interested in that. And yeah, I think that about covers most of what I wanted to talk about in ChemCAD. We have 15 minutes left. Okay, let me go ahead and wrap this up then. Okay, so we're managing uncertainty in our process design because we recognize that we're designing real processes and our mathematical models aren't always giving us the best prediction. But we can gain confidence in our model and gain confidence in our simulation and the outputs from our simulation if we work on managing uncertainty and thinking about what we're putting in and the steps that we're taking to manage uncertainty throughout the design process. And it's not only about getting great outputs and confidence in our outputs, but we're also working more efficiently, as you saw with the sensitivity study of the controller. Um, Sometimes we forget we have these tools available to us in ChemCAD, and we're working very hard instead of, I had a manager who used to tell me work smart, not hard. And that means like maximize your efficiency using the tools that you have available to you. Sometimes we forget these tools are there, but um, but we can really maximize our efficiency and our effectiveness as engineers if we're using the tools we have available to us. And the other thing is, building confidence in your results, because a lot of times you're bringing these results to stakeholders, and how confident are you in the output from your model? And then even most importantly is when you have put all this thought into your process, and you've used tools like ChemCAD to really be confident in your outcomes, it also enhances safety and compliance with regulatory controls on what we're doing in our process, and how we can sleep at night because we know we're getting good outcomes and good results from our simulators. So just to reiterate what we've talked about today, the best practice for managing uncertainty is to think about building our effective thermodynamic models before even building your flow sheet, doing that kind of background research, checking behavior, plot your TXY, do the azeotrope report tool to see if you have azeotrope forming and where they're forming and which models are predicting it accurately. So when we do all this kind of legwork in the before building the flow sheet part of the process, it helps with that confidence. It helps with that better, more accurate outcomes. And then after you start building your flow sheet, and again, data reconciliation, uh, you have a already built model with decent outcomes, decent behavior, realistic physical behavior being predicted by the simulator, and you just need that extra accuracy. You can use tools like data reconciliation, and then sensitivity analysis across the board. Use as much as you see fit, because it's definitely not a step after data reconciliation. It's used in the beginning, in the middle, and at the end of designing a process, checking outcomes, checking, variation, and building um, constraints or flexibility into a model as much as needed to manage the uncertainty we have um, with our process. So, in no particular order, this is just to wrap up all the things that are recommended to do. Um, just, as your flow sheet grows, still helps to continue to gather data and check how your model is doing, to impose constraints where needed to make sure that you've correctly captured in your operating envelope, basically, are we correctly simulating the behavior that we expect? Using sensitivity analysis to see, how are all these, once I've, started small and you build complexity and you have this big complex model, it's not always obvious how everything's interacting. So you use sensitivity analysis to try and figure out, if I vary this variable, like what are the outcomes from that? And you can do multivariable sensitivity analysis. It's a really great, really useful tool. And again, if everything's built and I'm happy with everything and it's looking great and I want to do now an optimization, again, sensitivity analysis can help you do that legwork before you use the optimizing tool to see, do I have optima? Where do I expect the optima? And yeah, so sensitivity analysis is like a very useful tool. across the board. And finally, last but not least, is something I hadn't talked too much about was contact the ChemCAD support team. Um, they're, I know I'm biased, but I really think that they are an amazing team. They're very helpful and they're very happy to hear from customers and to help customers figure out, how to get the most out of ChemCAD and how to get accurate behavior and outcomes coming out of their simulator. And so that's everything about ChemCAD and managing uncertainty in your process design. But um, if you are not that familiar with chem stations, this is just some background information. We're a global company. We are owned by DataCore, a process distribution software. And ChemCAD specifically is an intuitive process simulation software. It's used by all kinds of companies all over the world, research institutions, and we're helping engineers optimize their designs. And there's steady state and dynamics, and just a lot of um, usage out of ChemCAD and chem stations that we've been around for 30 years, and and we're in a lot of universities and research institutions as well. So just some background information about chem stations before we talk about the next steps. If you're already using ChemCAD, take advantage of our YouTube channel. You can watch our recorded webinars and tutorial videos. You can contact the ChemCAD support team anytime you have any questions, and they can help you find case studies and technical papers as well. They might have some recommendations for you on that. If you are not a ChemCAD user and you're interested in ChemCAD, you can contact us and we can give you more in-depth information and guided demonstrations. We have engineers who will help you demo your process specifically. And we can give you a free trial license for you to test these tools out that I've demonstrated for you today. Um, anyway, so that's the webinar for today. And thank you so much for attending. And I hope you found some valuable information. And even if you already knew these tools were in there, hopefully I at least got the wheels turning. And sometimes we have these tools available to us and we just uh, forget they're there, and we forget how we can take advantage of these to manage uncertainty in our process design. Um, all right. Let me see if I have any questions.
Hey, Noel, we had
Yes.
several questions. I answered most of the questions in here.
Okay.
Anyone has any other question, please type it in the Q&A before we end the webinar today.
Yeah. I'll go back to this since I cut it off short because I was worried about time, but we have a couple more minutes. But this was the Monte Carlo analysis of minimizing the power consumption of these compressors. Wow, this little bar from the Zoom toolbar is really getting in the way. Sorry. Okay, so like I said, we've already set up the independent and dependent variables, and we use this uniform real value, and we've asked it to generate 10,000 outputs. So if I click OK and run all, and it can quickly run 10,000 scenarios. It was a lot faster when I wasn't on Zoom, but um, wow, okay. Sorry, guys. It was running faster um, when I wasn't streaming. Let's see if it So with these results, we're visualizing where the optima are, if there are global and local optima. And again, optimization actually is a entirely separate webinar that I can go on about, how to best set up optimization. But now we can plot the results. I'm gonna plot it this way because I want to have both my pressure visualized in my plot, in my chart. Sorry. Okay, so now we can visualize kind of where these optima will be predicted by our optimization. So it's at like 400 and like 160. And I think because I ran the optimization, yeah, it's gonna go slowly too. It should predict then the same thing, like 400 and 160. So I've already set up the optimization and hmm, yeah, 392. And oh, maybe I was looking at the chart wrong. Like 187 and 392. Yeah, that's about right. So that's just to show you kind of the value of investigating before you run an optimization. It's not necessary, but it's just another way of using sensitivity study to visualize what's going on in your process and the expectations. Um, Up to you how you use these and how much you use these, but I just wanted to go over and show you the tools you have available to you. Was there any more questions then, Alejandra?
There's one more question in here. Can we do in the same matter feed model from literature and experimental data using ChemCAD by visualizing a graph? So the question here is that if you have literature or experimental data, can you actually put it in a chart so you can see it in a
Oh,
graph?
yes, yes, yeah. Um, this is probably not the best chart for me to demonstrate how to do that. But so you go to within the chart, and so this is during my I left this chart open from my I probably am gonna have to let me open a different simulation because it'll be harder to show. So my gas turbine example. Oh, I don't have the chart anymore.
Mhm.
Um, Let me just do a TPXY chart. Oh, I'm not gonna have, okay, here. I'll do my distillation TPXY chart. That will make more sense when I show it. That's what I'm trying to, like I could have done it in those other processes, but it just makes the most sense in this. So I'm running a TPXY. Um, so in TXY, okay. So if I have, for example, measured at my mole fraction of say zero point 0.3 and at 70 degrees, I can go up to within my chart, there's something called user series, and I can tell it to make a new user series. And I'm going to say this is like measured data. And my mole fraction, let's say it was 0.3. and my temperature was like 70, and this is just to show you. Okay, so I've created a user series and it's called measure data. And so now I can tell it to add my measure data to chart. And you can see here, um, it shows up as this purple dot. So if I have loads of data, I can, make a plot and check how my plot is doing with that. So in this case, I can say, it's not doing a great job. This is just pretend. I'm just making this up off the top of my head, but it can help you visualize for sure when you have measured data and you can input it into the plot. I hope that's the question you were asking. Does that sound right, Alejandra? Did I
Yes.
understand?
Thank,
Okay.
yeah. Thank you
Okay.
now.
All right. Yeah, we're over time now, so sorry about that. Anyone who's dropped off is going to get a recording of this webinar anyway. So, but thank you to everyone who stuck around and is still watching. I appreciate you attending this webinar. I hope you found it useful and yeah, have a great day.